Model 4. So we'll study the next bit, that is gas phase synthesis of nanomaterials. The gas phase synthesis of nanomethods are increasing interest because they allow elegant way to control process parameters in order to be able to produce size, shape, and chemical composition controlled nanostructures. Before before I select the few pathways for gas phase formation of nanomaterials, some general aspects of gas phase synthesis needed to be discussed. In conventional chemical vapor deposition, that is CVD synthesis, general products either are allowed to react homogeneously or heterogeneously depending on a particular application. In homogeneous CVD, that is chemical vapor deposition, particles form the gas phase and diffuse towards a cold surface due to atmospheric forces and can either be scrapped or form the cold surface to give nanopowders or deposited onto a substrate to yield what is called particulate films. In heterogeneous CVD, the solid is formed on the substrate surface, which catalyzes the reaction in a dense film is forced. In order to form nanomaterials, several modified CVD methods, that is, chemical vapor deposition methods, have been developed. Gas phase processes have inherent advantages. For example, an excellent control of size, shape, crystallinity, and chemical composition. High pure materials can be obtained. Multi-component systems are relatively easy to form, easy control of the reactions mechanisms. Most of the synthesis routes are based on the production of small clusters that aggregate to form nanoparticles. Condensation occurs when only the vapor is supersaturated, and in the process homogeneous nucleation in the gas phase is utilized to form particles. This can be achieved both by physical and chemical methods. Now, the furnaces, the simple fusion, the simple fashion to produce nanoparticles by its heating the desired materials in a heterogeneous crucible. In the heterogeneous crucible containing the desired material, this method is appropriate only for the materials that have a high vapor pressure at the heated temperatures that can be as high as 2000 degrees centigrade. Energy is normally introduced into the precursor by arc heating, electron beam heating, or joule heating. The atoms are evaporated into an atmosphere, which is either inert, reactive, or it may be the reactive. To carry out reactive synthesis materials with a very low vapor pressure have to be fed into the furnace in the form of a suitable precursor such as organometallics, which decomposes in the furnace to produce condensable material. The hot atoms of the evaporated matters lose energy by collision with the atoms of the cold gas and undergo condensation into the small clusters. There are three parameters which are controlling: the rate of evaporation, that is energy input; the rate of condensation, that is energy removal; the rate of evaporation, rate of condensation, and the rate of gas flow, that is cluster removal. All these three are the very, very important parameters. Okay. The next one is the flame-assisted ultrasonic spray pyrolysis. So in this, the precursors have nebulized and unwanted components are burnt in a flame to get the required material. Example, zircon oxide has been obtained by this method forming zircon. Flame assisted hydrolysis, that is a variant of this process, is used for the manufacture of fused silica. In the process, the silicon tetrachloride is heated in an oxyhydrogen flame to give highly dispersed silica. The resulting white amorphous powder consists of spherical particles with the sizes in the range of 7 to 40 nanometer. The combustion flame is synthesis in which the burning of a gas mixture, example, acetylene and oxygen or hydrogen and oxygen supplies energy to initiate the pyrolysis of precursor compounds, is widely used for the industrial production of powders in large quantities such as carbon black, formed silica and titanium dioxide. However, since the gas pressure during the reaction is high and highly agglomerated powders are produced, which is disadvantages of subsequent processing. The basic idea of low pressure combustion flames synthesis is to extend the pressure range to the pressure used in the gas phase synthesis and thus to reduce or avoid agglomeration. Low pressure flames have been extremely used by several scientists to study the particle formation in the flame. A key for the formation of nanoparticles with nano size distributions is exact control of the flames in order to obtain a flat flame front. Under these conditions, the thermal history, that is, time and temperature of each particle formed, is identical and narrow distributed towards. However, due to the oxidative atmosphere in the flame, this synthesis process is limited to the formation of oxides in the reactor zone. The next one is gas condensation processing. It's also called as GPC. So in this technique, a metallic inorganic material or the inorganic material, example suboxide, is vaporized using thermal evaporation sources such as crucible, electron beam evaporation devices or sputtering process in an atmosphere of 1 to 50 megabar. The helium clusters form in the vicinity of the source by homogeneous nucleation in the gas phase and grow by coalescence and incorporation of atoms from the gas phase. The clusters or particle size depends critically on the residence time of the particles in the growth system and can be influenced by the gas pressure, the kind of inert gas, that is helium, argon or krypton, and on the evaporation rate per vapor pressure of the evaporating material. With the increasing gas pressure, the vapor pressure and mass of the inert gas used, the average particle size of the nanoparticles increase. Log normal size distributions have been found experimentally and have been explained theoretically by the growth of mechanisms of the particles. One more in the complex processes such as low pressure combustion flame synthesis, where a number of chemical reactions are involved, the size distributions are determined to the log normal. The figure shows a schematic representation of the typical setup for gas condensation synthesis of nanomaterials, followed by consolidation in a mechanical press. Originally, a rotating cylindrical device coated with the liquid nitrogen was employed for the particle collection. The nanoparticles in the range from 2 to 50 nanometer are extracted from the gas flow by thermophoretic forces and deposited loosely on the surface of the collection devices as a powder of low density and agglomeration. Subsequently, the nanoparticles are removed from the surface of the cylinder by means of a scraper in the form of a metallic plate. In addition to this, cold in addition to this, the code figure devises several techniques known from aerosol since have now been implemented for the use in the gas condensation systems such as corona discharge, etc. These methods allow for the continuous operation of the collection devices and are better suited for larger scale synthesis of nanopowders. However, these methods can be used in a system designed for gas flow, that is, a dynamic vacuum is generated by means of both continuous pumping and gas inlet via mass flow controllers. A major advantage over conventional gas flow is improved control flow of gas particle size. It has been found that the particle size distributions in the gas flow systems, which are the log normal, are shifted towards normal average size value of an applicable reduction of the standard deviation of the distribution, depending on the flow rate of helium gas particles size are reduced by 80% and standard deviations by 18%. Now, the synthesis of nanocrystalline pure materials is relatively straightforward as long as evaporation can be done from the refractory materials. If the metals with the high melting points or metals with react with the crucibles are to be prepared, sputtering, that is, the zircon or laser or electron beam evaporation has to be used. Synthesis of alloys or intermetallic compounds by the thermal evaporation can also be done in the exceptional cases, that is, the vapor pressure of the elements are similar. An alternative sputtering from an external alloy or mixed target can be employed. Composite materials such as copper, tungsten, or gallium have been synthesized by simultaneous evaporation from the two separate crucibles onto a rotating collection devices. It has been found that excellent intermixing on the scale of the particle size can be obtained. Now, the next one, that is the chemical vapor condensation, that is CVC. As shown in the figure, the evaporation source used in gas process condensation is replaced by a hot water reactor in the chemical vapor condensation or CVC process. Depending on the processing parameters, nucleation of nanoparticles is observed during chemical vapor deposition of thin films and pose a major problem in obtaining a good film qualities. The original idea of the novel CVC process, which is schematically shown below, where it was intended to adjust the parameter field during the synthesis in order to suppress films formation and enhance homogeneous nucleation of the particle in the gas flow. It is readily found that the residence time of the precursor in the reactor determines if films of particles are formed in a certain range of residence time. Both particles and film formation can be obtained. Adjusting the residence time of the precursor molecules by changing the gas flow rate and the pressure difference between the precursor delivery system and the main chamber occurs. The temperature of the hot wall reactor results in the fertile production of nano-sized particles of metals and ceramics instead of thin films in CVD processing. Now, it is in the simplest form of a metal organic precursor is introduced into a hot zone of the reactor using mass flow controller. Besides, the increased quantities in this continuous process compared to GPC, that is gas process condensation, has been demonstrated that is a wider range of ceramics, including nitrides, carbides, can be synthesized. Thank you.